video, I will be giving a comprehensive tutorial on how to use OpenSCAD for a large-scale mechanical engineering project. I wanted to make this video because while there are plenty of tutorials on YouTube on how to do basic things in OpenSCAD, I haven't seen any tutorials on a large-scale project such as this. So I'm going to split this video up into three parts. The first part is I'm going to be going over the setup of all the software I have, the file structure of the project, and so on. The second part, I'm going to talk about the assembly that I built within OpenSCAD itself. And then in the final part, I'll be using two parts, the handguard and the upper plate, to go over all the all the functions that you would need to use to pretty much make any shape there is. All right, so let's get into it. So over here, I have IntelliJ Community Edition. I'm running the OpenSCAD plugin for IntelliJ, but I'm not using the viewer within the plugin itself since I found that to be fairly slow. I still use the regular OpenSCAD program itself since it's a lot faster and it's just easier to move around in the window. And I'm using FreeCAD here for generating step files. So to begin here, this tutorial kind of assumes that you have at least some basic programming experience. You don't need to be an expert, but I'll try to make it understandable for as many people out there as possible. So first things first, I have this project set up like how you would a typical software engineering project. I've got a README here, and it's got all the instructions, some basic information, renders of the whole thing, and parts list and so on. I'll be going more into like the engineering of like this rifle in like another video, like within the CAD setup. I'm not going to go over that in this video, otherwise it will be too long. Inside IntelliJ here, I have the renders here. I have three main folders. One is that contains all the code that's used to generate the files. And then the other two here, I have STL and step files. So I've made about 72 individual files or individual objects for this this build, and all 72 of them are rendered in STL and step file formats. So I just dumped them all into these folders right here, but since I'm primarily using the SCAD for my work, I've organized it hierarchically. So aside from the template and the util folder here, I've got everything's within the lower, and then if you expand these further, you can see that I have the barrel mounts all in this folder. I've got the forward controls, the brass catcher within the accessories of the lower, so it's fairly easy to navigate to wherever you need to go. And then the top level, I have assembly here, and that's what I used to generate this. So real quick, I'm going to show you how to generate a step file using OpenSCAD within FreeCAD. So what you want to do first is go to your preferences in FreeCAD, go to workbenches, and just make sure that OpenSCAD is loaded. I have already got it loaded, so I don't need to do anything here. And then the next thing you're going to want to do is go into your files and find the SCAD code that you want to use. Make sure you don't import an STL because that's based in triangles, and your step file is going to be really messed up. The CAM software is not going to like that. So just double click this. It's going to take a bit to load since this has quite a few shapes in it. For those who say that OpenSCAD is just like a toy and not really like a serious CAD software, I beg to differ since with this I've actually been able to machine all of these parts, and I'm actually holding a copy of this rifle more or less like in my hands right now. So, you just want to click the top level geometry, which is just this union here in this case. And then once you select it, you just hit export, and then I just dump it in my step file folder. So then, yeah, just change the name, and then click save, and then so on, and that's really it. I made another tutorial on this earlier. I think it's the first video on my channel. So I'm not going to go too much further into this. Moving on, so I'm primarily using IntelliJ as a text editor. I can format the text very easily. I can navigate to various files very quickly, and search the whole code base fairly easily. This code base has around 4,000 lines of code. About 3,500 of them are actually like the core code, and then the rest of it is just sort of libraries and stuff that I've written to sort of help me debug it. The next thing I'm going to go over is the assembly. So if you look in this file here, this is what I'm using to generate this image you see on the right. So I have some parameters up top, and these are what's used to sort of configure it. So if I want to change this, if I want to explode this, first of all, I can just change this to a 1. And then as the option here says, and then now the whole thing blows up, and then you can see in detail like all the springs and the roll pins and so on, where everything goes together. Again, I'll go over all of this in more detail, but some of you might be wondering why I didn't just use a Boolean operation here. And the reason why is because I can, by using a scalar value, I can set it to something in between, like 0.5, and then sort of have it like, in an in-between, or I can blow it up even further than I want, and just have it spaced out a bit more. But yeah, so I'm going to leave it back to the fully assembled one right now. And then the other benefit of this is you can also animate it, although with this particular assembly there's about 121 parts in it, so it's quite slow. Other configurations I've made are, for example, this is currently the 556 configuration. I can also do the DPMS configuration. I have this set up to be like the 6.5 Creedmoor sniper variant of this rifle. And I can also change it to the sniper variant's handguard very easily with that by changing this parameter right here. I can take the bolt carrier in and out of the bolt in and out of battery. I can change the ejection port accessory to the brass catcher. There you go. And I can also make it, I can also remove the accessory. So, you don't really have to have anything on there, but I'm just going to revert this back to what it was. I can also open and close the dust cover. So it was open earlier, now it's closed. And then for each one of these things, I have like a sub-assembly in there. So for example, there's the upper receiver, there's the cheek riser, the fire control module, and so on. And then I just pass on the exploded parameter. And then if I look inside each one of these, it's basically sort of like the same thing. So I can edit each one of these sub-assemblies manually. And it sort of functions exactly the same way. Of course, I also can choose which handguard that this wants to be rendered in based on what I pass in right here. So in this one, I'm using the extended. But the other cool thing is I can also animate this thing blowing up. So to do that, I just switch our exploded variable to T, $T, and then I start this at 0. I'll do 10 and 10 FPS in steps. So once I click play, you'll see that time will loop from 0 to 1, and then it'll take steps of 10 at like 10 FPS or something. I don't think that's actually 10 FPS. It's a little slow, but yeah, that's basically how that works. So I'm gonna revert this, and then let me just show you like another one, like the dust cover. So I can animate this opening up the same way. So you can see like the rod pushing the dust cover lips open. And then let's see here, I also got the fire control module here loaded up. So pretty similar. And then the other thing about IntelliJ is I'm using Git as my source control. And you can notice that the blue is the files that I've made changes to, as you just saw me typing in it. So I can, just look at the diffs very easily, and I can just, push and commit. I'm using GitLab for my to host my repository, and I'm also sharing that with a few people that I'm working with on this. So yeah, since I'm mostly the one who's working in SCAD, I just do everything in the master branch. There's not really much point in doing pull requests and all that if I'm the only one here. So yeah, I think that that wraps up the assembly that I'm using here. If I want to like open this up and sort of hide parts of it, I can just comment out these things very quickly, and now I can look at like the bolt carrier and then the sears going together and stuff like that. So yeah, that's what we got there. All right, let's move on to the more in-depth tutorial. So I'm gonna load up the handguard here. And so over here I have the code that's used to generate this shape right here. So this file is about 109 lines long. A lot of that's just taken up by the imports and the headers and so on, and the comments. So probably maybe like 90 lines total. So first thing you notice is when I did the preview here, you'll see that you have like these fuzzy lines over here. This is something called ZFighting. You're gonna want to, if you want to get rid of this, you just have to make the difference you're using to cut it open like larger by like 0.01 millimeters or something like that. But I usually don't bother with that since once you click render, it goes away. I don't really use the preview for much at all. One other thing before I forget is when you set up OpenSCAD, make sure you're using the nightlies because the last release candidate was from 2021, and it doesn't have the newer rendering engine. I forgot where it was in here. Advanced. Oh, right here. So the old one is Seagull. That's what it is set by default. And then the last release candidate forces you to use that, but the newer ones have manifold, and this is a lot faster. So if I didn't have this enabled, this is pretty much I can render this instantaneously, but the old one would take like 1 or 2 minutes to render this. So just make sure you got that turned on and you're using the latest nightly. Okay, so with that out of the way, let's go over the code here. So if you notice the imports at the top, I'm importing a few libraries. So I did the same thing in complete over here, except I used the use over here. So the difference between use and include is include basically takes everything that's in this file and it just pastes it into the current page that you're in now. So for example, rounded cube, it basically just takes everything here and pastes it into here. Whereas use only copies in the modules. So for example, it would ignore this and it won't automatically call this function. It will just pull in the module here. So you have to call the module yourself, like I'm doing on line 35, for example. So back to handguard, I'm importing all of these modules at the top. Rounded cube is one that I'm using a lot. So I wrote a bunch of these modules for rounded cubes. Like this one is just rounded on one axis, and then this one is rounded on all 3 axes. And I also use this one to generate the M-lock slots. I'm not using these ones in this repo, but I do use it in some other projects like the integrated foregrips, where I need to generate the bulges for the M-lock, and that basically just relies on the rounded cube in here. So the other thing is you're going to want to make sure that you define modules for everything. So a module is basically like a function, and then you can pass in parameters like the handguard length and the extended length that I'm using here. So if you look at this file right here, I'm doing the same include. I guess I could also do use here, it doesn't really matter. But all I do is I just call handguard and I say I want this part right here to be 190 millimeters. So if I measure it, it should say exactly 190. And then the forward part is 112 millimeters. So if I measure from here to here, should say that. So because I did this, I've set everything up to be very parameterized. So if I want to shorten it, I can do 180, and the whole thing will get shorter. I guess I messed up a little on the end over here, but let me just take it down to, let's say 150. So this is probably what I'd want to use if, let's say I had a shorter gas system and I wanted this opening over here to be a bit closer. So I have mine set up for a rifle length gas system. So to shorten it, I can just take this thing down, let's say for a carbine length system or pistol length and so on. And then this is just for like anything beyond that. So for the sniper variants, you know, I think I set this to like 160 or something. So, you know, the fore end is actually quite long. Yeah, that's how the modules work. So you're gonna want to do that in as many different places as you can. Going on down, I have a union and a difference. So union basically means that everything in here just gets merged. And then difference means that the first object you have in here is the base object, and then everything after that is iteratively subtracted from the first object. So, you know, this is pretty much like the core of what I'm using here. Typically, usually you'd want to limit the number of nested unions and differences. But in this particular case, there were some things that required me to have it nested, mostly like these bulges at the end, which needed to be unioned with this. And if I put the bulges that I have at the bottom here within the top difference, then like the part that gets extended into the handguard would get cut off. Yeah, usually what I do is I have like a root level difference and then a union, and then I put everything in the union and then it's like just start subtracting stuff outside of that, which is sort of what I do here, with the exception of everything that is outside the difference. Mostly the Picatinny rail, and the alignment knobs. You're also going to want to make sure that your root level operation is like a union or a difference or a hole. And the reason why is because it just makes it easier to select in FreeCAD like this. You don't really have to. I guess you could just select the whole thing like that. But this is just a habit that I've always had. So the other thing is you're going to want to like define local variables everywhere. So this one is the QD offset, and that's basically the distance from the front to the center of the QD holes. So if I change this to like 10 or something, you can see it moving closer. If I change it to 20, it'll move further away. And then, you know, if I double click on it, you can see where it's highlighted here. So I have like the bulge for it. And then, you know, outside the union, I have this difference here. And then I'm calling the QD cut function that I wrote that's in util right here. So it's just a small couple liner. And then for the main body of this, I'm drawing a polygon and then extruding it. So, you know, the linear extrude here is the handguard length, you know, pretty simple. That's what we wanted. And then I'm mirroring it on the y-axis. And the reason why I'm doing that is because I only want to have to draw each one of these points once. Since it is symmetrical along the y-axis, I'm just mirroring it across. So the extended rail, I'm basically just doing the exact same thing. Both of these are rotated because like normally this would be flat on the XY plane and it would be going up. So I had to rotate this to go forward. It's just easier to look at. And then for this one, I've translated it forward. So the translation is another very common, you know, function that you're going to use. So for this one, since the forward one is going to have to be, it's not at the origin, it's going to have to be exactly the handguard length. It's going to start at the handguard length, right? So I just translated it forward by that amount. And then the rotate, you know, pretty standard, just like, you know, 90 degrees on the x-axis and then 180 on the z-axis. Same thing that I'm doing above. And then, yeah, these are the points that I'm using. I define like a bunch of variables, such as the upper width and the upper height and so on. Those all live in the constants function right there. And, I just have it like sort of printed declaratively in the file. And then, it just gets pasted into this file. Of course, the other thing is I also made sure to put comments explaining what each block of code does. This makes it really easy for me to go back and edit the spots where if I just haven't touched it in a while, I'm not as familiar with the code anymore. I can quickly go and say like, okay, this line right here, cut for the gas adjustment. That means that's for this part right here. Or the M-lock cuts. Okay, this is what goes. This is what cuts like all of this stuff right here, and that goes on, for this part right there. So moving on down, this right here cuts out the interior. So it's really the same thing as what's above. I just made everything like 2 millimeters inward. So you can see that it's pretty much the same shape. I just sort of copy pasted it. And yeah, now we're moving on to the M-lock cuts here. So in this part, I'm going to use this example to demonstrate the for loops. So for loops are pretty common in programming. You can use the same thing here to sort of do repetitive tasks. The starting offset here, this is a function I defined for just how far from the end that we have here. It's pretty much the same thing as the QD offset here, so I'm basically just saying start at 42 millimeters from the beginning. I put it down here because it's it's not really used outside of like this particular spot. So you always want to make sure that your variables are defined in a way where the scope is only visible to the functions that need it. The space right here is basically saying like space each one of these M-lock slots 40 millimeters apart. That's according to the official M-lock specification on Magpul's website. And then the slots here, I'm just doing some math to calculate how many slots I'm going to be cutting total. I'm using the floor method, which is basically just round like a decimal value down to the nearest integer. It's just the math like handguard length, extended length, minus the offset, and so on, divided by the space. I don't think I have this down perfectly, but it sort of works for this example, so I'm not going to waste too much time messing with it. We go to the for loop here, the actual for loop itself, and this is basically saying for our iterator, start at 0, and then go up to the slots with 1 as the step. Since we're counting the number of slots, I'm just going to make it 1. Sometimes I go from 0 to 1, and then I change the iterator from like the step to like 0.1 or like 1/6 or something, and then like you just have like the 6 be like an n value so that you can change the definition. But here I'm not doing that. I'm doing that in the bolt carrier, and that's how I cut the cam pin. So for this block here, this is everything that's running alongside the entire handguard. So the sides, the bottom diagonals, and then the bottom itself. I'm just cutting the M-lock slot that I showed you earlier right here. Again, this is from the official Magpul specs. Like the other ones here, I'm just rotating it based on the angle of the handguard itself. And then This block here, this is for the ones that are just on the main body, and then this one is for the ones that are on the extensions. So again, I'm doing some more math here. So I'm using the floor method and like a slightly different formula to calculate this. So for example, since this is not the entire one now, like we can't include the extended length here. So it's the same formula as this, but I just removed the extended length from that value. And then, so it stops a bit earlier. As you can see, that's the ending. And then for the extended one, I sort of did something similar, except I start off by using the floor, and then the end is the same as what we have above. So, well, actually, I think I can probably just replace this with slots. Oh yeah, I can. So I guess I duplicated some code there. And then the other thing here is for the extended parts right here, I used an if statement. So I'm checking if extended length is equal to 0. And if it is, just like, basically ignore this whole block. And that's so that I can set this as 0. So like the basic version of the rifle that I actually made is actually like this, just a lot cheaper. So this works fine in OpenSCAD if I don't have these blocks right here, and same for here, for example. But the problem is when you go into FreeCAD, it's going to give you or OpenSCAD is going to give you a bunch of issues. Like OpenSCAD is generally a lot pickier when generating the step files than the STLs, so you're going to want to be really careful about writing like high quality code to generate those, since what works in OpenSCAD may not necessarily work to generate a step file. So yeah, moving on, we got our alignment knobs, just a rounded cube, pretty standard. And then for the side knobs, that's what I'm using for the screws. So I'm actually I have another function for a Torx cutout that I drew. And it, the countersunk Torx screws go in there, and that's what holds the handguard in there. And then the top, I have a pick rail. I just used another function to generate that based on the handguard length. Again, this is just the main handguard length. We don't want it running along the whole ones. Like this handguard's sort of based off the MREX rail that for the SCAR. I think Kinetic Development Group makes that. And then on the front, I have like an angled cube that I'm just subtracting out to make this little ramp. And then yeah, that's pretty much it for this this file right here. So the next file I want to go over is this upper plate right here. And if I go here to show you the code, you can see it's fairly similar. I'm doing extrusion over here, but the only difference is, there is one function in here that wasn't present in the last one that I think is extremely useful, and that is the hull. So a hull basically means like just wrap everything within it. Like let's say it's like shrink wrapped, right? Like you don't necessarily have to do this. So like in this particular case, I'm using it to cut out like these angles on the sides here. And let me just show you what that looks like. So if I pull this out and just paste it in the bottom here, you can see like that part that was missing Let me translate this out. So basically, I'm just taking this shape right here and cutting it out of the side. And the reason why, so these points right here, I'm using these 4 cubes that are basically just like, you know, very, very small pixels, right? And then I'm just basically wrapping it to generate the faces. Now, there is another way to do this in OpenSCAD that's a bit cleaner. That's the polyhedron method. But the polyhedron method is very difficult to use. It requires you to first define all of these, and then you have to get all the vertices in order, and then define the faces, which is very very time-consuming and mentally difficult to do. With this, all you have to do is basically just specify the coordinates, which is just lives in this translate. So you want to generally be careful with the hull. It works fine in OpenSCAD, but again, it is a little glitchy sometimes in OpenCascade. Again, it's fine if you're just doing 3D printing, but if you're going to do any CNC, you need to have those step files, and you're going to have to be a bit more careful with the code you write. Previously, I had an issue here where if you notice, like, these two are symmetrical on both sides, so I did the same thing by mirroring, like, this, for example. I mirrored these, and OpenCascade did not like that for some reason. It works fine for the extruded polygons, but when you have a hull nested inside of it, it just really doesn't like that. So just be careful with that. The other thing is, I mentioned this in like one of my other videos, is you basically just don't want to have any sort of circular or spherical shape within a hull, because that just gives you like a line segment error, and it divides that rounded surface into multiple or many infinitesimally small line segments, and then any CAM software out there has generally had a problem with that, SolidWorks or whatever else. So that was something that took me a little bit of time to figure out. So yeah, now you know. Let's see here. So the other thing, sometimes what I like to do is I just like making these a little, getting rid of all the excess new lines. It's just easier to read. Oops. Yeah, I didn't want to get rid of that last one. And then I just hit Option Command L, and it just reformats the whole thing for me. So based on everything, at this point, I'm just going to go to my commits here. So I'm going to look over my changes. So these were the ones that I made earlier, just in for demo purposes. Same with this, so I'm just going to get rid of them. Same with this one, get rid of that. Keep the formatting changes. Yeah, I'll keep that change. And yeah, so at this point, I'll just do this, and then say formatting, and then I'll do commit and push. And that's it. So this is pushed up to GitLab now. Yeah, I think this video is getting pretty long now, so I think I'm gonna cut it off here. In the next one, I'll probably go over more in depth of like how this thing all works. I know I've made a lot of YouTube videos of me sort of putting it together. Some people have said that they've had a hard time understanding what was going on. Because I was wearing gloves, or the lighting or the angle wasn't as good. So I'm hoping that the exploded diagram here is going to make it a bit more easy to understand. So, stay tuned for that. I'm spending a lot of time right now working in the machine shop to finish making the last couple of parts I need for this thing to work. So whenever I have time, I'll get on the computer again and record another video. In the meantime, please follow me on YouTube, or subscribe to me on YouTube. Like this video, helps with the algorithm. Please follow me on X. I'm not a huge fan of social media, but X is really the only site that I've been using that hasn't, deleted my posts or banned me or taken down my videos for saying things that they don't like. And I also post on X more frequently than Reddit and any other places. So if you want the most timely updates, just follow me on there. So yeah, I'll try to have the other video out in a week. So please subscribe. Have a good one.